Okie dokie. So, the way that we name and draw amides is very similar to the way we name and draw esters. So do keep that in mind. Hopefully you guys figured out that link. In fact, a lot of the ester questions are very similar to the amide questions. So that's also good news as well. You guys haven't seen a secondary amide, so I do want to show you how to deal with this. Hope you're okay. Yeah, you haven't seen one of these secondary ones. You've seen a lot of primary ones, which are just this guy, and it's basically the amides at the end. In this case, the amide is in the middle of the molecule, so we need to specify what is where. So first thing I'm looking for is the parent chain, which is this half here, the pent and amide. So pent, telling me that there are 5 carbons. So 1, 2, 3, 4, 5. I'm just making sure I have enough space for everybody. The next thing I then look at is the functional group. It tells me you have an amide. So amides, just as a reminder, is that C double bond O and a single bonded nitrogen over here, like that. Are we good so far? Okay. Next thing I then need to draw is the branch coming off of it. So this is something new that we haven't seen before, and that is the N-methyl. What that is trying to tell me is that you have a methyl group attached to the nitrogen. CH3. It's very similar to how we name our esters, whereas if it was an ester, there would be that single bonded oxygen, and that would be your alcohol tail, and then this would be your carboxylic acid tail. Carboxylic acid takes the parent chain, the alcohol takes the branch naming. So in this case, same idea, but instead of just going methyl, we're actually going to attach the N to indicate that the methyl is attached to the nitrogen. It's something that is unique to the amides that we don't need to do for the esters for some reason. Not sure who decided that rule. It's not like you have to go O methyl for esters. So I don't know, unique thing that's happening. And then the last thing we do is fill in our hydrogens. Nitrogen, be mindful, can have 3 bonds. So there should be 1 hydrogen here. I think you might have, I missed that when I was checking your work. So 1 less hydrogen for the nitrogen. Then this one here, this one here has 1, 2, 3, 4. It's done. This one here has 2, that one 2, that one 2, that one 3. So that everyone has all 4 bonds. And that's how we deal with those ones when they're a little bit more complicated. The other reason why I wanted to point this out is because, and this is actually a really good page in the side path that you guys were doing, how to make these secondary amides. So be mindful because they can ask you to convert into that, and I'll show you guys a question like that because it's nasty. It's within the realms of what they can ask, but it's not a nice one. Are we okay with that? Cool. All right, so I'm going to pause it here because I want you guys to do, I think, some more pre-learning. I don't think you guys are quite ready yet. I think you guys could use some time. I'm just trying to see what time we got. Go away. Shall we do like 20 minutes and then do notes? Does that sound good? Just to do some final touch-ups, just to make sure you understand it, and then I'll show you guys an exam question. Cool. All right. Once again, I'm learning that hindsight is a great thing, and I keep realizing things I should have taught before other things, which is okay. One of the things that I haven't had a chance to talk to you guys about, organic chemistry people, is the different types of addition reactions, or I should say, different types of polymerization reactions. I haven't had a chance to cover that, but I know it was in the side pad, so I do want to cover it. All right, so just as a reminder, when we are talking about polymerization, we are talking about making repeated molecules. There is actually 2 different ways you can do this. I'm just going to add some extra backtrack notes. Polymerization. So we're just making a repeated long chain molecule.
Stay on the stair with your bag, please.
So this could be like hundreds, thousands of lengths in chain. It could be really, really long. We also did talk about it briefly about how depending on what you have attached in that polymer, it can result in different properties. Say, for example, we have a hard plastic versus a soft plastic. These are both polymers, but they are different types of polymers because they have different properties. Now, something to keep in mind is that there's two different methods to making this. The method that we've talked about so far is the condensation method. So the condensation method is joining the monomers together by removing water. That's why we call it condensation, because one of the byproducts is water, condensation. So far we've talked about this condensation method in two ways. We've talked about it in the form of esters, and the way they form is by a carboxylic acid and an alcohol. So the carboxylic acid is losing the hydrogen, no, the hydroxide, and the alcohol is we're losing that hydrogen. You could also make, or sorry, let me keep going. So that's how we're making our esters. If we're making an amide or polyamide, you have a carboxylic acid again. But in this case, the alcohol swapped out for an amine, and the amine is again providing that hydrogen. So those are the two different ways we can make it. Move that, move that, move that. Sorry. Are we okay with that so far as ideas? Just checking the room just to make sure people look like they are following along. Also be mindful we can swap out the carboxylic acid for an acid chloride. That's a really good way to speed up our rate of reaction because we know acid chlorides are very, very reactive. In this case, the byproduct won't be water, it will be hydrochloric acid instead. Because instead of the OH, you have a chlorine. Cool. So that's one method in our polymerization is, like I said, removing water and then joining all the links together. The other one, which isn't talked about as much this year, but just in case, I want to make sure we cover our base, is the addition method. This method is covered in level 2 chemistry, not in level 3, but just in case it pops up, I do want to just remind you, or sorry, I just want to teach you guys what this is because I'm mindful you guys haven't done this before. The addition method is using alkenes. So that's C double bond C, like that. And the way we join the alkenes together is you have multiple together, and what's going to happen is you break the double bond, and then you can join the two monomers together. So you have an alkene, you break the double bonds, and add monomers together. When I talk about monomers, I'm just talking about the individual units that we put together. So this was an alkene, we broke the double bond, we then joined the two together. It's unlikely they will ask you about addition polymerization, but it is technically fair game because it is from the level 2 chemistry book. Every so often they might be nasty. I have seen, like I said, I'll show you what I mean by I've seen a nasty question 2022 that I didn't like, but it was actually fair to ask. So that's why I just want to cover it just in case. I have also seen it on the mock exams. They ask you to compare and contrast these two different types of reactions. It's also probably useful for some of the excellence level stuff just to show that you understand what's happening in this reaction. All right, questions, concerns, or comments? All right, I'm going to pass out this exam question that we're going to look at now. So the good news is the amides are very similar to the esters, with one exception. One for each. Cool. We're ready to move it? All right. Move my camera. There you go. Okie dokie. Here is now how you will probably get your amide questions. The first one here, so something to keep in mind is they often pair the amide questions with the dipeptides. They could also pair it with a polyamide. So it's just like a polyester, it's just a repeated amide unit. They also love to also pair this question with the optical isomers because the amino acids can make up an optical isomer because it has 4 different things attached to it. So don't be surprised if that question's often paired with it. Are we hopefully okay with what I was just saying? It wasn't all jargon. Okay, cool. So expect to make them and expect to break them. You should be able to go in both directions when it comes to this question. This time they've given us the dipeptide and they want us to figure out the 2 amino acids that make it. So it's a nice little refresher for you guys, especially for bio kids. Proteins are made up of amino acids. There are, I don't know actually how many amino acids we got. Let's see. Amino acids. How many are there? I'm guessing there's 20 by the quick Google. Let me show you guys the images. Here we go. So just a reminder what amino acids are. Oh, good. It even gives you information. So here's a polypeptide chain, also called a polyamide, is fine as well. You have all these little amino acids that join together to form a nice long chain, and then depending on the sequence, it will fold into a protein. It's very specific on the sequence that it folds in because you need to have certain properties next to each other. And then there should hopefully be a chart. Oh yeah. This is the basic function, the basic organization for an amino acid. Again, the word amino acid is hinting to you what function groups are there. Amino, that's the amino, and acid from the carboxylic acid. So an amino acid has both the amine group and the carboxylic acid group. That's why it got its name. It also has a hydrogen, and then it has a side chain that is variable, and that changes the amino acid and thus gives it its unique properties. So, oh my goodness, so many pop-ups. This is an example of all the different amino acids that we find in our bodies. As you can notice, they have different sort of side chains on that R group, which is that guy over here, and that's going to give it that variety of properties. And depending on the sequence, these guys interact with each other to make that 3D shape that we know for our proteins. Something else to keep in mind with these guys is that most, all but one, will form optical isomers. So the reason why I say they form optical isomers is because they have 4 different things attached to it. It has the amine group, it has the carboxylic acid group, it has a hydrogen, and then it has an R group. If the R group is hydrogen, then it has 2 of the same, and it doesn't form optical isomers. But everything else will form an optical isomer. What's the interesting thing for us is that as humans, I believe we only use one orientation, because remember how one goes clockwise, the other one goes counterclockwise in polarized light? We use one set, and the other set is completely useless to us, which is really interesting. Different organisms, I think, can use different ones, depending on the setup of the organism. So that's just a fun fact. Anyway, that's what we're looking at for the amino acids. Questions, concerns, or comments? All right, back to there. So this is a dipeptide. The word di, like you guys have seen before, means 2. And then peptide is just another way that we refer to as the amide component. So we have 2 amino acids that are joined together by an amide bond, also known as a peptide bond. They want you to first to circle the bond to show where are these 2 amino acids linking together. And it's linking over right here. So you're just basically trying to find the amide. All right. The next thing it asks us to do is to do hydrolysis. So just like when we were doing ester hydrolysis, we are breaking it apart. The point where it's going to break is where the nitrogen is. Just like when we talked about the esters, it was a single bonded oxygen. So it's going to break right here. And that's how we're going to get our 2 amino acids. I'm not going to do the whole justification because I want to not talk too long, and I don't think you guys wanted to hear me go on and on and on. It does want you to go through a bullet point of all the different information. For example, explanation of what hydrolysis means. So giving that information of hydrolysis is using water to break apart a molecule. Also comparing and contrasting the similarities and differences between acid and base hydrolysis. So what happens if we do the hydrolysis in an acidic solution versus a basic solution? The acidic solution could be anything generic, such as sulfuric acid or hydrochloric acid, so long as it's dilute. For a basic solution, again, any base works. Sodium hydroxide, potassium hydroxide, all of those are fine. Cool. So the main thing they want you to do is to show what the products are in both reactions. So I'm going to skip the justification because I figured you guys are probably okay with it. Is that a head shake? No? No? All right. So main things that we're looking for here is an explanation of hydrolysis. So hydrolysis is breaking a molecule apart with water. So one half of the molecule is going to get the OH, the other half is going to get the hydrogen. So just like we were talking about the making of polyesters or polyamides, we are doing it with condensation. We're joining molecules together by removing water. So if I remove water to join, I add water to break. Just opposite. All right? The main difference to keep in mind is what's happening with acidic versus basic conditions. So in acidic conditions, you're using something like hydrochloric acid or sulfuric acid also works. Any acid works. This should be dilute. If you're doing something in a basic solution, then you can use something like sodium hydroxide, or another one is potassium hydroxide. Again, you just want it dilute. So it just helps with the addition of the water when we have it acidic or basic. Are we okay so far? All right, something to keep in mind with acidic solutions is that this is going to neutralize the base. So in this case, since we're talking about amides, it's going to neutralize since we're talking about, amides, it's going to neutralize the ammonia bit of it. If we're dealing with an acid, if we're dealing with a basic solution, it's going to neutralize the acid. So the carboxylic acid. So it's something to keep in mind. It's different than esters. With esters, the only thing that was getting neutralized was the carboxylic acid half. The other bit was an alcohol, and the alcohols were unaffected because the alcohol is not acidic or basic. In this case, the amide has both an acidic group and a basic group, so we have to be mindful of those guys neutralizing. All right? So when we go look back at our dipeptide, this here is a base component because that's the amine. That here is the carboxylic acid, so that's the acid component. That here is the amine, so that's going to be the base component. And that bit here is the carboxylic acid, that's the acid component. So when I break these two molecules apart, let's break them and then figure out how we're going to tinker with them. So first off, with an acid. So let's first draw the molecule, and then I'll add some extra hydrogens when we need to. So here's my first one. We just copy and paste what we have up here down here. So let me zoom that out so you guys can see the whole thing. So I'm going to draw this first molecule. It's the C, the H, the CH3. I have an N. We're doing an H. I'm just going to draw it expanded so we can see how everyone's going. That's a carboxylic acid.
Wait, so I'm going to get into like base acid base.
We're cutting it into two amino acids, and then we're going to neutralize it. So that's the drawing for this guy up here. I'm just going to zoom it out so you guys can see the whole thing. Oh, there we go. So I've just taken this half of the molecule out and redrawn it over here because we're breaking the two apart. Because there's two amino acids in that. It's dipeptide. Just trying to find another color that I want that I haven't used yet. Orange. All right, this is the other one. So I would draw carbon. It has a hydrogen. It has an alcohol. It has the carboxylic acid. I'm going to draw it extended so that way we can see its neutralization. It has the amine, like that.
Why do you say amine and not amine?
Because it's an amine. Amines just have the nitrogen with the two hydrogens. Amide is the carbon with the nitrogen and the carbonyl. So the difference in the word, yeah. So that is an amide. This is an amine. Okay? So I've taken that molecule and I've broken it apart. I was just showing it so you can see how I broke it apart. So the answer is literally on the piece of paper. All you need to do is break it apart. Isn't that crazy? Answer's there. All right, since this is acid hydrolysis, what that means is that I have a lot of extra hydrogen ions. So the hydrogen gets attached to the base. In this case, it's going to get attached to the nitrogen. And then it forms a little positive because it has an excess. So that's it neutralizing the base. For the base hydrolysis, you're drawing the exact same thing. The only thing that changes is now you're neutralizing the acid. So let's redraw our molecules. I'm going to start abbreviating it because I think you guys are okay. So let's draw the molecules initially, and then we can fix it. You can draw it condensed or you can draw it big. Whoopsie. Oh, that's fine. I saved it. All right. Now, in a basic solution, we have lots of OH minus. So that OH minus is going to start ripping off hydrogens so that it can neutralize it and become water. So it's ripping off this guy, and it's ripping off that guy. Oi! I'm actually recording this lesson, you know that, right? Does that make sense? So that's what's being produced when that gets neutralized. It's not affected because that is an alcohol. If it was a carboxylic acid, then yes. And that would be a mean question to ask you, but that would also be fun. Because when you look at all those function groups, there are function groups that have acidic components to it, so it could happen. But that is not, it's a good question, that is not a carboxylic acid. So alcohols are unaffected. That's why when we did the ester hydrolysis, the alcohol and the ester was unaffected. Well, hopefully not too bad. You guys aren't abandoning me. Esther looks happy, that's good. Do you want to see the marking schedule for this question? And then I'll do the back. See how the points broke down. I'm pretty sure there must be some in here that are acidic. Yeah, there are some nasty ones in here that do have chains that are acidic and chains that are also basic. They shouldn't give you something that hard on the exam, though. I'd be very upset if they didn't.
They can.
They can. They shouldn't. But it can happen. I haven't seen it. All right, what are we on? A minus. Did I link the answer? I think I did. Yes, I did. All right, let me just show you guys the marking schedule for this so you guys can see how actually organic is not that bad. All right, that one I think, what was on page 7? So where are you? You're up here. There you go. Okay. So here's how the points broke down. And I hope you guys are starting to realize that this is crazy how they give the points. Circle around the peptide bond. That was an achieve point. Yes, I know. All right, here is the justification that I was talking about. So water is being used to break the amide bond, split into 2 molecules. This is obviously a nicer answer than I did, so do write nicer answers than I do. But the main thing that you're needing to keep in mind when you're looking at that is that, oh, they did add a lot of extra details that I totally forgot that you guys should probably include. I was rushing. So acid hydrolysis uses dilute acid, such as sulfuric. Basic hydrolysis is using some dilute base, such as sodium hydroxide. They both require heat under reflux. Again, heat helps speed up the rate of reaction. Reflux helps trap any volatile solutions that come off. It ensures a 100% reaction. The amine group is going to get propanated, or neutralized is another way to talk about it, in the acidic conditions where the carboxylic acid group is going to get deprotonated, also known as neutralized, in the basic solution. So that's just the justification. Not a whole lot. It's a couple lines. And then these are the drawings of the various products that I was showing you guys. So just adding the extra hydrogen and the nitrogen for the acidic, and then taking away the hydrogen in the base. Here's how it goes crazy. All right. Describes hydrolysis or draws two amino acids. That's an achieve point. The merit point is explain hydrolysis using either reagents or proton transfer and draws two correct structure formulas. So you basically had this justification plus two molecules, any of these two. And then 4, no justification whatsoever, just draws all 4 molecules correctly. If you just drew all 4 of these correctly and didn't write anything for the little paragraphy bit, you can get a merit point. And the answer is on the page. The answer is on the page. What I'm talking about. Organic's ridiculous. Is it law?
Oh, yeah.
Yeah. All right. Let me go through the last rant. The excellence point is explains hydrolysis and draws all the structural formulas for the 4. So yeah, that's all it was. So organic's very strange like that. What? I said if you had drawn all 4 of these correctly, no explanation, you get a merit point. If you had explained it and drawn all 4 correctly, excellence point. I don't understand how, but it is. All right. Crazy. Huh? This is the 2022 exam. It's the same. It'll be similar. There's a lot of like easy give me questions. That's why I said organic's easy to get the excellence on. It's hard to get them achieved on because he's such a steep learning curve. But once you got it, it's fine. Yes. It'll do something similar on the exam, yes. All right. This is what I mean by you also need to go in reverse. So keep in mind, this is the Kevlar question. Don't be thrown off by the benzenes. Just redraw them. It's just a hexagon with alternating lines. Or you can draw it as a hexagon with a circle in the center. Bye. Like that. Both of those are fine. All right. I'm going to try to keep it short because I'm mindful of the time and I'm mindful I don't want to talk too long. So, these are my 2 monomers. Remember when we were talking about esters, you had 2 choices. Either you have both function groups on one molecule, you have 1 monomer, or you have 2 monomers and both of those function groups have both of them. All right? So, this one is the exact same idea. You're just joining it together. When you join it together, you're going to take off the hydrogen, you're going to take off the chlorine, and then you're going to branch these 2 guys together. That's it. Some follow-up questions. Why does each monomer need 2 functional groups? In order to form the polymer, you need to be able to attach monomers onto both sides. If it's only on one side, then you stop the chain. Yeah? I'm not going to write it down because I want to save time. Using the box below, draw the Kevlar chain showing 2 repeated units. So, this is not 1, 2. The set is 1. So when I go to draw it, we do the closed brackets. We do the nitrogen with the hydrogen. We draw, is it not showing? You draw the benzene, like that. You draw another nitrogen that has a hydrogen. You then connect it to this molecule here. Like that. And that is your amide link. Oops, did not draw that right. And then you do it another time because they want you to do 2 repeats. So you got this guy again. Nitrogen, H, C double bond O, benzene, C double bond O. And then that's the end of that chain. Like that. 2 repeated units. And then this one wants you to explain the type of reaction that's forming the Kevlar. Again, it's just a condensation polymerization. So it's basically like the same one before. You're getting asked that question twice. All right. I'm trying to be quick because I'm mindful of time. Let me show you the breakdown of that question. That was question 3. That's the answer. Extend the chain in both directions to form a polymer. That's the drawing. This is the condensation reaction, blah, 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 blah. Give me that definition. Again, crazy points here. Achieved. Recognize the chain needs to be extended in both directions. Draws a polymer with one minor error, or with the amide linkage. Identifies condensation. All of those are achieved points. The merit point is draw 2 correct repeating units and explains condensation. So basically it was these 2 bits. And then the excellence was all of it. So this also was an excellence point, which I think is crazy, because I don't think it's that bad. Some other things I want you guys to keep in mind before I forget, is when they ask you to draw dipeptides, they will give you 2 amino acids. They will ask you to draw 2 dipeptides. The only thing you're doing is you're changing the R group around. Because if this guy goes first and this guy goes second, that's one thing. And if that guy goes first and that guy goes second, that's another peptide. So just keep in mind, it's a trickier question than it actually is. So since we're talking about dipeptides, the order that the amino acids go in changes the chain. So just keep in mind when you're drawing them, you have them one way around, and then you flip around the R groups. Okay? So, but you guys will see them on the CPR quiz that I've given you for that question. All right. Something else I want to point out to you guys, because it was an awful question, is, it was up here. Here we go. All right. So the do now question I got from this one here, this is one of the conversion questions we talked about. It's not on No Brain Too Small, because No Brain Too Small only goes up to 2020. This one wants you to convert 2 bromo... Oh, wait. Shh. Still talking about class. 2 bromopentane. And they want you to convert it to N-methylpentanamide. So just be mindful. This one's a nasty question, but also a fair question. So they can ask that. So the trick for this one would be converting the haloalkane first into either carboxylic acid or in acid chloride, and then adding the primary amine. The 9th question, the hard question. All right? So that's what we're looking at, and that basically covers all of our organic chemistry material. Friday's lesson, I'll give you guys another day on conversions, because I'm just mindful it's a nice summary, and also I taught it in the wrong order. Keep in mind that I have made you guys a CPR quiz for amides. I haven't printed it out because I'm trying to save paper. If you want to print it out, I'm more than happy to print it out. But you see what I'm saying? They've given you 2 amino acids, and they want you to draw 1 dipeptide and then the other dipeptide. It's not a trick question. You just put them in the alternate order. So alanine goes first, and then the thymine, and then in the other one, thymine goes first, and then the alanine. That's all. And then same setup. Explain what hydrolysis is. It's very, very repetitive. And this one's also crazy because they ask you to do the hydrolysis of the dipeptide, and they've given you the amino acids. So you just got to copy these amino acids down here and then add the hydrogen or remove the hydrogen. So, steep learning curve, but it's actually not that bad once you get it. Questions, concerns, comments? That covers everything in organic chemistry. It is now balls in your court to get everything learned. Okay? So, week 8, we will do an exam, full exam. We will do it in here, because I'm also running a thermochemistry workshop. Once you get that done, you can join the thermochemistry workshop, if you're doing both. But like I said, you got to pass both. And hopefully you guys have an idea whether or not you want to do both after seeing everything with organic. It's this all over again with thermochemistry, with the level of content you got to learn. So ask yourself, do you really want to learn all this material again in a different context?